Chapter 3, Visualizing Data. Section 3.1, Why Visualize Data? I am a huge fan of visual representations of data. And not just me. Anyone who works with data agrees that data visualization is one of the most important ways to understand and communicate your data. There are several reasons why you should visualize data. For one, visualizing data allows you to identify patterns that might be difficult or impossible to detect by looking at numbers or labels. Second, the brain is an amazing pattern recognizing machine, and we are visual creatures. In fact, about a third of our brain is devoted to vision, and even more the brain is closely related to vision, such as visually guided movements. So put the data in a format that nature shaped our brains to process. Third, looking at data can reveal outliers, mistakes, or other issues that could introduce artifacts or negatively impact the analyses. Fourth, showing data in graphs can help non-experts understand the important take-home messages from the analyses. In other words, proper data visualization allows you to craft a data narrative and communicate that narrative to others. Finally, data are beautiful, and beautiful things are worth looking at. To illustrate the importance of visualization in understanding data and mathematics more generally, consider the following equation. This is equation 3.1. It is the quantity x squared plus y squared minus 1, that quantity cubed, minus x squared times y cubed equals 0. There is a figure associated with this equation, and if you are reading along with the book, then you actually have to flip forward to the next page to see the graphical representation. It forms a heart. The xy pairs that satisfy the equation I just read aloud form a heart, and the point of this demonstration is that just looking at an equation might not necessarily give you any meaning or any insight. It's just very abstract and mathematical. But mapping that equation onto a visualization can reveal patterns in the equation, in the math, that you cannot understand purely by looking at the equation or at the data. Okay, so that's just a cute little example. Section 3.2, How to Visualize Data. Not all data can be visualized in the same way. Appropriate data visualizations depend on the data type and the way you want the data to be communicated and interpreted. Data visualization is a skill. It's not a difficult skill, but it's one that you master through learning and practice. The reason why data visualization is a skill, an art really, is that some kinds of data have intrinsic properties that prescribe how they can be visualized. For example, populations in different zip codes can be displayed as color on a map, whereas other kinds of data do not intrinsically lead to a particular visualization. Hence, we must decide which visualizations can and should be used for different data sets. This is not trivial and can be challenging for large multivariate data sets. So with small data sets, you can simply look at the entirety of the data. As an example, I recorded the times that I started eating dinner each night for a week. Figure 3.1 shows those data in a spreadsheet. This is literally the entire data set, and so visualizing the data is as simple as looking at the numbers. Figure 3.1 is a screenshot of a spreadsheet which shows two rows. The first row is the day of the week, Monday through Sunday. The second row is the time that I started eating dinner. The actual times don't matter, the data don't matter in this case. It's just an example of how, with a very small data set, you can literally just look at the entire data set. However, most data sets, and dare I say, all data sets that you will ever work with in this book, other books and courses, and in real-world applications, are considerably larger than this. They contain hundreds or thousands or possibly millions of rows and dozens or hundreds of columns. Important patterns in the data might be difficult or impossible to see simply by eyeballing the raw numbers. The point is that looking at raw data can be useful and informative, but graphical data representations are more insightful, more aesthetic, and more interpretable. In the rest of this chapter, you will learn the most common data visualizations, what they look like, how to interpret them, and what kind of data you can use with them. You will also see myriad examples of data visualizations throughout the rest of the book. Section 3.3, Bar Plots. Let's start with an example. Imagine that we conduct a survey in which we ask people where they get their news. This is all fake data that I made up for this example. Their choices are TV, newspaper, internet, or word of mouth. We can calculate the percentage of participants who responded yes to each of these options. Figure 3.3 shows the results of our survey visualized as a bar plot. The ticks on the x-axis correspond to the categories of news sources, and the y-axis, or the height of each bar, corresponds to the percentage of people responding yes to that news source. Note that the x-axis represents a categorical variable, while the y-axis represents a continuous numerical value. So figure 3 shows a bar plot. There are 4 bars corresponding to the 4 media types. So that was TV, newspapers, internet, and word of mouth. And we see that TV gets about 40% responding yes, newspapers around 10%, internet is around 85%, and word of mouth is around 20%. So those percentages correspond to the heights of the 4 different bars. Bar plots are suitable for nominal data. Now, keep this in mind when learning about histograms, because bar plots and histograms might initially look similar, but they are used in different situations. Also, notice that the percentages across the bars do not sum up to 100%, because people can get their news from multiple sources. This will be contrasted with pie charts and percentage normalization of histograms, which you'll learn about later. A few additional and more general remarks about visualizing data using bar plots. First, the axes have labels that tell the readers what is being shown. Second, each tick mark, that is the small cross marks on the axes, is labeled on the x-axis. The labels can be rotated to fit longer labels or for aesthetic style. The ticks on the x-axis are equidistant, and that makes the graph look clean. The order of the categories on the x-axis is arbitrary. This is an important point. There's no reason why newspapers must be left of internet. There are multiple ways to sort the category, for example, by the period in history when those sources were developed, or by their popularity, so that would be sorting according to the y-axis values. Those are choices that we make. They are not intrinsic to the data. The y-axis limits in the bar plot are reasonable given the data range. So imagine, for example, that the axes were drawn from a minus 500% to plus 6,000%. Now, some kinds of data are naturally bound. For example, height cannot be negative, and other kinds of data are not naturally bound. The limits of the axis should extend slightly beyond the range of the data, so that it is slightly below the smallest value and slightly above the largest value. The title at the top of the graph is short and informative, and in this example, there is no color. The physical version of the book is printed in grayscale, and I did that to minimize printing costs. If you make data visualizations that people will print out physical copies of, try to avoid using color. But, if your graphs will be viewed only on digital devices, or that they will be printed in color, then color can help make the graphs look nicer and the graphical elements easier to distinguish. I'll get back to this in section 3.12. To create a bar plot in Python, you specify the x-axis locations and the heights of each bar, which is the y-axis. For example, the code below creates figure 3.4. So in the code, I import matplotlib.pyplot as plt. I create variable y to be a list of the numbers 1, 4, 3, 9, and the variable x is a list of the numbers 0, 1, 3, 4. And then I use the command plt.bar x, y. That creates a bar plot that I show in figure 3.4, which has 5 marks on the x-axis for 0, 1, 2, 3, 4, and 4 bars corresponding to the y-axis values that I specified. Now, there is no bar shown at x equals 2 because the x variable does not have a value for 2. It has 0, 1, 3, 4. Creating a bar plot in R is the same idea, but the syntax is a little bit different. Here I use ggplot. Section 3.3.1, bar plots for grouped data. Let's keep working with our news sources study. Now let's imagine we surveyed 2 groups of people, millennials and boomers. Footnote. Millennials are people born between 1981 and 1996. Boomers are their parents who grew up amidst the largest global increase in wealth, education, and living standards, and who invested heavily in their retirement funds instead of clean energy technology. End footnote. We can now separate the responses according to younger versus older respondents. How should we visualize the data? There are actually 2 ways we can group the bars. We can group by age or by news source. Both are shown in figure 3.5. Importantly, the data are exactly the same, but the interpretation of the results differs. I will discuss the differences between these 2 plots in the next paragraph. Before reading that paragraph, please inspect the figure and think about the narrative being conveyed by each grouping. Figure 3.5 has 2 panels showing 8 bars in total. Each panel has 8 bars. In panel A, we have the bars grouped by news source and then separated for millennials and boomers. So we have 4 pairs of bars that are adjacent to each other. So for example, we have TV, and then the black bar shows millennials, that is around 10%, and boomers right next to it in a gray bar, and that's around 85%. Then there's a small gap, a small white space, and then there's another 2 bars that are touching each other for millennials and boomers for the category of newspapers, and then same for internet and word of mouth. In panel B, we are grouping by generation, so by age group. And here the x-axis has 2 groups of bars that are touching each other, and the 2 groups are millennials and boomers, and those 2 groups of 4 bars are separated by white space. So in panel A, the narrative is about the differences between age groups. For example, you can see, if you were looking at the figure, you can see that millennials get more news from the internet compared to boomers, whereas boomers get more news from TV. Here's a footnote reminder that these are fake data I made up just for this illustration. End footnote. But in panel B, the narrative is about how people get their news within each group. For example, you could see that millennials get more news from word of mouth than from newspapers. That information is present in panel A, but it is less obvious. Importantly, neither representation is correct or incorrect. You will need to choose how to group the data based on the research question, the purpose of the study, and the finding you want to communicate with your audience. I won't show the code here for creating grouped bar plots because that is one of the exercises at the end of this chapter. But I do want to explain more conceptually how grouped bar plots are created from a matrix of numbers. So in Python, plt.bar, the function plt.bar, groups bars by rows such that columns within a row will have adjacent bars, while each row will be separated by a blank space on the x-axis in the bar plot. Therefore, grouping bars the other way around is done by transposing the data matrix to swap the rows and the columns. In R, you can create a new data frame using the mutate function. This is visualized in figure 3.6. So figure 3.6 has 4 panels organized into 2 columns. In the left column, we see a visual depiction of a 2x4 matrix, a matrix with 2 rows and 4 columns. And that produces a bar plot where there are 2 groups, and each group contains 4 bars with no spacing between them, and then spacing between the 2 groups. And then in the right-hand column of this figure, we see that same data matrix is transposed. So this is now a 4x2 matrix. So 4 rows and 2 columns, and the corresponding bar graph underneath that matrix has 4 groups of bars, and each grouping has 2 bars that are touching each other. And the idea that I'm depicting in this figure is that the same data can be grouped in bars in different ways, which may facilitate different interpretations. Section 3.3.2, Error bars. Error bars are a natural extension of bar plots. An error bar plot looks like a bar plot, but, well, it has error bars. The error bar is the vertical line in the center of the bar. There are often horizontal hash marks to help you see the top and the bottom of the error bar. See figure 3.7 for an example. Figure 3.7 shows 3 panels. Panel A is a bar plot where you see just bars. There are 6 bars with various heights. Panel B shows an error plot, so there are no bars here, there are just dots. And then there are vertical lines that extend above and below each dot coming off of the x-axis. And panel C shows an error bar plot, which is the combination of a bar plot and an error plot. So in panel C, you would see 6 bars, and each bar has a dot in the middle, horizontal middle, on the top of the bar, with vertical lines extending above and below, indicating some measure of variability. Back to the text. Error bars can represent several different quantities, such as standard deviation, standard error, and confidence intervals. Now, on the one hand, any quantity visualized by an error bar will be somehow related to variability, but on the other hand, the different quantities can lead to different interpretations, which means that error bar plots can be confusing or misinterpreted. Well, the solution is simple. Always clearly indicate the data characteristic that the error bars show. Error bars are calculated from a mathematical formula that are not always constrained by reality. For example, imagine the bars in figure 3.7, this is the figure that I just described, represents the height of buildings in different geographical regions. So the error bars for categories 0 and 1, which you can see when you're looking at the figure, actually extend into negative. Now, that has no physical interpretation and yet is the result of a formula. The point is that error bars are informative but can also introduce confusion if they are not explained clearly. Section 3.4, Pie charts. A pie chart looks like a circle with wedges cut into it. In other words, like a pie. Pieces of the pie correspond to data categories, and the area they take up corresponds to the percentage of the whole. Percentage of the whole is the key to knowing when to use a pie chart. A pie chart is interpretable only when the data can be transformed into percentages that sum to 100%. For example, the bar plots in the previous section that was showing the categories of news sources cannot be represented using pie charts because their sum exceeds 100%. However, a change in the survey questionnaire could make the data appropriate for a pie chart. Imagine the survey contained a single question that asked people where they get most of their news. Now, respondents can provide only one answer, and the sum of percentages for each type of news source will equal 100%. Figure 3.8 shows an example of a pie chart. So figure 3.8 shows a circle with wedges cut into it. This is illustrating fake data from this news source study where we asked respondents their primary source of news. So the biggest proportion of the pie is the internet, that is 70%. Newspapers is a small wedge, that's 5%. TV is 15%. Word of mouth is 10%. All of those numbers sum to 100%. Back to the text. Pie charts are for categorical or labeled data. They could be ordinal or nominal. The primary restriction is that the data must be convertible to a percentage of the whole. Section 3.5, box plots. Box plots, also traditionally called box and whisker plots, are similar to bar plots in that they show categorical data on the x-axis and continuous data on the y-axis. But whereas bar plots reveal only one feature of the data, the average value, box plots show several additional distributional characteristics that allow for better interpretations of the data. Figure 3.9 shows a box plot of random data that I simulated. There are letters in the figure indicating important features that I will describe in a moment. Now, you may encounter some new terms in this list. I will describe these in more detail in the next chapter. So figure 3.9 illustrates an example box plot. There is one long or tall rectangle in black, and there are thin vertical lines that extend above and below that black rectangle. And then there are arrows pointing to different locations of that box plot, with each arrow corresponding to a letter that I will now describe in turn. So A, the horizontal line corresponds to the median of the data. The median cuts the data in half such that 50% of the data are below the median and 50% of the data are above the median. In the figure, the median is illustrated as a thin white horizontal line that goes through approximately the center of the black bar. B, the lower edge of the box demarcates the lower 25% of the data. In other words, 25% of the data have values below the edge of the box. C, same as B, but for 75% of the data. Another way to say this is that 25% of the data have values larger than the top edge of the box. So taken together, 50% of the data are contained in the boundaries indicated by the box, while 25% of the data are below the box and 25% of the data are above the box. This middle range of data values is called the interquartile range, abbreviated IQR. D corresponds to the arrow pointing at the bottom of the thin vertical line that comes down from the black box. This is the data non-extreme minimum. The horizontal hash mark at the bottom of the line is the smallest data value that is not considered an outlier or an unusually extreme value. E indicates the same as D, but for the non-extreme maximum. The letter E in the figure points to the thin horizontal line at the top of the vertical line. F in the figure is pointing to a circle that is well above all of the other features of the box plot. So this is indicating an outlier. Outliers are unusually large or representative data values. Outliers can be difficult to define precisely and deal with responsibly. You will learn a lot more about outliers in chapters 4 and 7. Box plots are useful because they provide a sense of the distribution of the data and can help identify outliers or problematic data. Box plots can also reveal interesting patterns of data between categories. For example, figure 310 shows a pair of box plots of two categories. Perhaps these data represent monthly salaries for the same profession in different countries. So although the data have the same central value, country A has a wider spread of salary compared to country B, which kind of indicate a larger potential for salary growth. Figure 3.10 shows two box plots in the same figure. They both have the same median approximately, but the box plot on the left, which is labeled A, has a much broader range, so larger variability, and the box plot indicated in B to the right is like squashed down. Section 3.6, histograms. Histograms initially look like bar plots, but differ in several important ways. The most important distinction is that bar plots are made from categorical data, whereas histograms are made from numerical data. Let's start with a simple example using a small data set of integers. So here we have data set, I call this data set X. It contains the following integers: 1, 2, 2, 3, 3, 4, 5, 5, 5, 5, 6, 7, 7, 7, 8, 8, 9. So it's just a bunch of integers going from 1 to 9. So there is 1, 1, 2 2s, 2 3s, and so on. A histogram is the visualization of the numerical element on the x-axis and its count on the y-axis. Figure 3.11 shows a histogram of this integer data x that I just described. Take a moment to inspect the x-axis tick locations and labels. Are they placed where you expected? Now, in the figure, you see that the leftmost tick mark is 1, the rightmost tick mark is 9. That feels immediately intuitive because the data contains integers 1 through 9. However, the tick marks are not placed in the centers of the bars. They seem to be kind of sporadically located. So when you look at this figure, you probably think that these are incorrectly placed. So are the tick marks placed where you expected? I guess the answer is no. I guess you expected the tick marks to be at the center of the bars. And that would actually correspond to a bar plot, not a histogram. This is a subtle but important distinction and is crucial to understanding how to interpret and construct histograms. Now inspect figure 3.12. Notice that the bar heights are exactly the same as in figure 3.11, but the tick marks are centered in the bars where you probably expected. So now figure 3.12 looks just like figure 3.11, except that each bar has a tick mark exactly in the center of the bar, and they are labeled according to the integers 1 through 9. Before explaining the difference between these two figures that differ only by the x-axis locations of the tick marks, let me first explain where your confusion comes from. You looked at the data or listened to the data set description, thought about counting the number of ones, the number of twos, the number of threes, and so on, and then expected the histogram to show those counts. In fact, you were expecting the histogram to be a bar plot. That is not how a histogram works. A histogram works by defining numerical boundaries and counting the number of data values that fall between those boundaries. Figure 3.11 and figure 3.12 look different because I used different boundaries for the binning in the code. So figure 3.13 shows the two sets of boundaries. So when you looked at dataset X, you counted the number of ones and the number of twos and so on. But the histogram in figure 3.11 was created by counting the number of data values between 1 and 1.9, and then the number of data values between 1.9 and 2.8, and so on. So figure 3.13 has two columns that show the boundaries of histogram bins used in figure 3.11 on the left and figure 3.12 in the right column. So the boundaries are 1 to 1.9, 1.9 to 2.8, 2.8 to 3.7, and so on up to the final bin boundaries of 8.1 to 9. So that was for figure 3.11. That was the figure where the x-axis tick marks are not where you would expect them to be. And then in figure 3.12, where the x-axis tick marks are directly underneath the bars, centered in the bars, the boundaries are 0.5 to 1.5, 1.5 to 2.5, 2.5 to 3.5, and so on, down to the final boundaries of 8.5 to 9.5. Back to the text. Another difference between figures 311 and 312 is that the former has the x-axis ticks on the boundaries, while the latter has the x-axis ticks in the centers of the boundaries. This difference is important for visualizing multiple histograms, as you will soon learn. Now, I realize that this discussion might be confusing, and it's probably even more confusing if you are listening and not also looking at the figure. But if you take the time to grasp it, then everything else about histograms will make sense. This is a worthwhile effort because many data analyses, assumptions, and interpretations are based on the shape of the histogram. Now, not all data sets comprise a small number of integers. What if we had more numbers with higher precision? For example, imagine a data set comprising the lengths of 500 Babylonian mongooses. Footnote 4. The plural of mongoose is, disappointingly, not mongoose. Plural of mongoose is mongooses. End footnote. So if we measure lengths with the precision of a millimeter, it's unlikely that there will be even one exact repeat in the dataset. So we simply cannot use bar plots the way we could have used bar plots with the integers dataset. Our only option is to define boundaries and count the number of data points between those boundaries. And that's a histogram. You can see an example of this in figure 314. Figure 314 shows a histogram of mongoose lengths. The data are fake, but the range of numerical values is accurate. So these are random data that I created. The data range that you see on the x-axis is between approximately 25 centimeters and 55 centimeters. And the counts range from about 5 to about 27. It has a slight normal distribution, so there are a little bit more data values clustered in the center around 40 centimeters. There's also a margin note where I write that binning continuous data is also called discretizing data, as in to make the data discrete. Back to the text. Just by looking at the histogram, we cannot know the exact lengths of the mongooses, only the numbers of data points that fall within the boundaries defined for each bar. Now, this means that we have lost information in the visualization, although this is balanced by the gain in interpretability. In fact, data visualization often entails some loss of information, and the art of data visualization comes from knowing what and how much information to sacrifice in order to increase interpretability and pattern discovery. Now, why did I choose those boundaries and not different boundaries? I could have added more bins, thus adding more bars, which would have resulted in less information loss. Indeed, the more bins you use in a histogram, the more information is preserved. There is some arbitrariness in the choice of the number of bins, which I'll get back to in a moment. But first, let's agree that too few bins, or too many, is not desirable. Consider figure 315, which shows histograms of exactly the same data using few versus many bins. So figure 315 has two panels, panel A and panel B. Panel A shows a histogram with only 3 bins, so there's only 3 bars in this histogram, and you see that they are basically equal heights. The third one is a little bit lower. And then in panel B, we see a histogram with 300 bins. And here it is also difficult to interpret because we just see lots of vertical black lines without really being able to determine the shape of the distribution. These two panels also differ considerably in their count. So in panel A, the histogram with 3 bins, the counts are around 150 or so. And in panel B with 300 bins, the counts are somewhere around 2 to 4. Back to the text. Clearly, there are extreme bin count options that are not very useful. but that still leaves a wide range of acceptable bins. So how do you pick the right number of bins? There are several guidelines that you can use to compute the number of bins. These guidelines are based on characteristics of the data set that you will learn about in the next chapter, and so we will return to this discussion in the future. For now, it's fine to pick an arbitrary number of bins based on visual inspection. 30 to 40 bins tends to work well in many data sets. In figure 3.14, that was the distribution of mongooses that I first described, I used 30 bins. Concerning distribution tails, one piece of terminology you must know. The sides of a distribution, when represented as a histogram, are called tails. There is a left tail and a right tail. If the data have negative and positive values, these might also be termed the negative tail and the positive tail. This paragraph refers to figure 316, where you see an idealized histogram. It's a bell curve, and you see shaded regions to the left and to the right, indicating the left tail and the right tail. Back to the text. These are somewhat loose terms in that there is no specific boundary that separates the tail of a distribution from the body of a distribution for all distributions and all analyses. Sometimes the tails are described qualitatively, other times the tails are exactly defined using boundaries such as a percentage of the area of the distribution or a specific numerical value. Later in this book, I will refer to analyses as one-tailed or two-tailed. The former means only one side of the distribution is considered, while the latter means that both sides of the distribution are considered. Section 3.6.1, Histogram versus bar plot. The key difference between a bar plot and a histogram is that bar plots have categories on the x-axis and histograms have numerical ranges on the x-axis. To know whether you are looking at a bar plot or a histogram, ask yourself if it would be possible to shift around the bars on the x-axis. Think back to our news sources study and the mongoose study. There is no reason why the internet bin must be to the right of the newspaper bin. We could swap the locations of those bars on the x-axis and it would be fine. However, the locations of the bars in a histogram cannot be swapped. The 40 to 41 centimeter bin clearly belongs to the left of the 41 to 42 centimeter bin. So, in a histogram, you cannot change the order of the bins and preserve interpretability of the plots. This is no trivial distinction. The shape of a histogram is used to determine whether the data were drawn from certain distributions and whether certain statistics can be applied to those data. So at the risk of redundancy, I will reiterate this important point again. With a histogram, the ordering of the x-axis is meaningful because it reflects an intrinsic property of the data that have to be discretized into bins by defining boundaries between successive bins. And with a bar plot, the ordering of the x-axis can change. Some orderings may afford better interpretations, but the order is a choice made by the data analyst, not dictated by an intrinsic property of the data. Section 3.6.2, Counts versus Proportions. The y-axis of the histograms and bar plots I've shown so far represent raw counts. Raw counts can be useful because you can see exactly how many samples are in each bin. But raw counts have some disadvantages, particularly when comparing datasets that have different sample sizes. An alternative is to convert the counts into proportion or percentage. Consider figure 317, which shows the same data in raw form on the left and transformed into proportion on the right panel. So figure 317 has two panels, panel A and panel B. The bars correspond to a histogram of some fake data that I generated. The relative heights are the same. The x-axis locations and tick mark labels are exactly the same. The difference is that panel A on the left shows raw counts. The y-axis ranges from 0 up to around 90. And the histogram on the right in panel B shows proportion on the y-axis. And there, the y-axis ranges from 0.0 up to around 0.45. Back to the text. Importantly, the shape of the distribution as well as the relative bar heights are the same before and after normalization to proportion. The key difference is the numbers on the y-axis. Neither of these methods is better. They simply convey information in slightly different ways. Figure 318 contains a comparison of counts versus proportions and when you might prefer each option. Figure 318 is actually a table. It has 2 columns and 4 rows. The first column is labeled raw counts. The right column is labeled proportion. So raw counts are meaningfully interpreted. They are difficult to compare across data sets. The values do not need to sum to 1, and therefore they are better for qualitative inspection. Proportion in the right column of this table requires more effort to relate to the raw data. It's easier to compare across data sets. The values sum to 1 or 100%, and therefore they are better for quantitative comparisons. Back to the text. So how do you convert counts into proportions? The formula is straightforward and involves assigning the value of each bin to be itself divided by the sum over all bin counts. This is illustrated in equation 3.2. Here we have each bin converted to proportion as the bin in raw counts divided by the sum of the raw counts over all of the bins. So the sum over all of the normalized bins will be 1, and converting from proportion to percent simply involves multiplying proportion by 100 and attaching a percent sign after the number. Here is an example of where converting the histogram to proportion is advantageous. Revisiting the mongoose lengths, imagine that we wanted to compare African to Asian mongooses. So I took a research trip to Mauritius and measured the lengths of 100 mongooses, and you went to Java and measured the lengths of 500 mongooses. And yeah, I admit it, I didn't work hard enough on my trip. Anyway, figure 319 shows the histograms of lengths from the 2 islands. So figure 319 shows 4 panels arranged in a 2x2 grid. On the left side, we have the counts of African mongooses on top and the proportion of African mongooses on the bottom. And on the right column, we have the counts, so raw counts of the Asian mongooses and the proportion of Asian mongooses on the lower panel. Everything is a histogram. And what you see is that because we measured so many more Asian mongooses compared to African mongooses, it is difficult to directly visually compare the 2 distributions in raw counts on the top row. However, when we convert to proportion in the bottom row, then we can directly visually compare the proportion of African mongooses to Asian mongooses in terms of their length. And what you see in these bar plots is that the African mongooses tend to be a little bit shorter and more clustered around 30 to 40 centimeters, and the Asian mongooses tend to be more evenly distributed between around 25 and 55 centimeters. Now, these are fake data that I generated for this diagram, so don't overinterpret the conclusion. Back to the text. Now, the heights of the 2 raw counts histograms cannot be directly compared. Our sample sizes are different, so the heights of the bars are necessarily different. On the other hand, we do not care about the absolute y-axis values if the question is whether African or Asian mongooses are longer. So normalizing both histograms to percentages allows us to compare the distribution heights and shapes quantitatively. Now, to compare these two distributions statistically, we could use a t-test or a KL test, but that is beyond the scope of this discussion here. Section 3.7, lines versus bars in a histogram. Histograms have bars instead of lines because all data points that fall between boundaries are in the same bin. Discretizing the data involves some information loss, and we no longer know what the data would look like if we had used different boundaries. So this means that you should use bars, or dots or any other discrete marker, with a vertical drop between neighboring bars. Why are lines between bins inappropriate in a histogram? The problem with lines is that they imply a smooth transition between points, as if you knew what the data would show had you changed the boundaries for the binning. On the other hand, if the sample size is large and the distribution is fairly smooth, then the implicit assumption of smooth transitions is usually reasonable. But we should strive for accuracy when possible and allow violations of accuracy only when the benefits outweigh the costs. This paragraph refers to Figure 320. Figure 320 shows an example of the risk of using lines versus bars. There are two panels, panel A and panel B. Both show histograms. Panel A shows a histogram with 3 bars, and panel B shows a histogram with 4 bars. In panel A, we see 3 bars with lines, straight lines, connecting each of the pairs of bars. Now, the bar heights go from being low to high and back to low, and the line from the high middle bar to the low rightmost bar has a circled dot halfway in between the two bars, with an arrow labeled assumption. The idea is that the line gives this implicit assumption that we know what the data would look like had we rebinned the data. And panel B, in contrast, shows 4 bins, where the third bin is now idealized to be somewhere in between the second and third bin from panel A, but instead of being in between the high bin and the low bin, it's actually higher than the second bin. So the reality does not match the assumption which is implied by the line connecting the two bars. Back to the text. That said, there are cases where lines facilitate an interpretation and visual aesthetic that bars cannot achieve, and you will get to explore this in exercise 5. The conclusion is that histograms are most accurately displayed using bars, but lines can be used when the gain in interpretability outweighs the risk of giving the false impression of smooth continuity between discretizations. Fortunately, the more bins in a histogram, the more accurately the lines represent the shape of the histogram. Concerning lines in bar plots, it should be obvious that using lines in a bar plot is never appropriate. Going back to the new sources example, what would it mean to have a line drawn between internet and word of mouth? It makes no sense to imagine an interpolated data point between these categories, particularly considering that the ordering of the categories is arbitrary. Section 3.8, Violin Plots. One of the advantages of using lines instead of bars is that it allows you to visualize data in a violin plot, which is both an excellent and a beautiful way to show data. A violin plot is created by plotting a histogram using lines and swapping the x and y axes. This paragraph refers to Figure 321. Figure 321 shows the mechanism of creating a violin plot from a histogram. There are 4 panels. Panel A shows a histogram of some data, looks like a normal distribution. The histogram in panel A has bars. In panel B, the title is interpolation, or step 2, to interpolate. And here we see a smooth, curvy line that looks a bit like the histogram in panel A. The idea is that we are redrawing the histogram using a continuous line instead of discretized bars. In panel C, the title is Step 3, Rotate and Mirror. Here we see that we have swapped the x-axis and the y-axis, and so now the y-axis shows the data value, which used to be on the x-axis in panels A and B. The x-axis in panel C shows count, which is normalized, and we see that the curved line in panel B that goes smoothly up and smoothly down, referring to the normal or bell curve distribution, is now starting at the center of the x-axis, and it curves out to the right and then back towards the center. And that's mirrored on both sides. So it's a little bit like a leaf or like a violin. There are also black dots depicted in panel C to show all of the individual data points. Finally, panel B shows an example of an asymmetric violin plot where the left lobe and the right lobe are not equal to each other. They are not symmetric. Instead, they are showing different distributions from different data sets. Back to the text. You will often see the histogram mirrored across the vertical, which gives the violin plot its symmetric look. If you have two data sets, you can create an asymmetric violin plot with each data set taking one side of the plot. This is shown in figure 321D, which I just described a moment ago. You will learn how to create this asymmetric violin plot in exercise 7. Asymmetric violin plots are suitable when the two data sets contain related data that have comparable ranges. For example, imagine an asymmetric violin plot that shows heights of adult males and females. In this case, the data feature is the same, height, and the range of the data is comparable for both groups, men and women. A counterexample would be an asymmetric violin plot for annual salary in dollars per year and height in feet. These two features are distinct and numerically very far apart, and putting them in the same violin plot would only cause confusion. One final comment on the dots corresponding to individual data values in figure 321. This is what I described in panel C. Adding small random x-axis offsets helps with the visualization. Otherwise, the dots are plotted on top of each other. Section 3.9, Linear versus Logarithmic Axis Scaling. The y-axis of many graphs can be displayed using linear scaling or logarithmic scaling. Figure 322 illustrates the same data in a linear scale in panel A versus a logarithmic scale in panels B and C. Panels B and C show actually the same line and the same scaling, but using different y-tick label formatting. So figure 322 is a comparison of linear y-axis spacing with logarithmic y-axis spacing. There are three panels. Panel A shows one line directly across the diagonal. The x-axis goes from 0 to about 50, and the y-axis goes from 0 up to 10,000. The label on the y-axis is spacing by addition. Then we have panel B, which shows the same function, but it's not a straight line anymore, it's a curved line. It goes up very steeply, and then there's a bend, and then it goes up, it continues to increase, but at a much slower rate. Here, the y-axis tick marks go 1, 10, 100, 1,000, and 10,000, and the y-axis scaling says, the y-axis label says spacing by multiplication. The data shown in panel C are the same as what I just described in panel B, but the y-axis ticks look different. Here it is in scientific notation. We have 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4. Back to the text. What is the difference between linear and logarithmic scaling? It's all about the spacing between tick marks on the y-axis. On a linear scale, the spacing between tick marks is based on addition, while on a logarithmic scale, the spacing between tick marks is based on multiplication. Notice that each y-axis tick mark in figure 322A, that's with the linear scaling, is 2,000 plus the previous tick mark. However, in figure 322B and C, that is with the logarithmic y-axis spacing, each tick mark is 10 times the previous tick mark. The implication of this difference is that really large data values appear compressed. Of course, the numerical values are the same. This is simply a matter of visualization. When should you prefer logarithmic over linear scaling? Logarithmic scaling is useful when the data involve exponential growth or decay. Examples include population dynamics, bacterial growth, stock market growth, and radiation. Lots of data visualizations in biology and physics benefit from logarithmic scaling. That said, most people without a scientific background are more comfortable interpreting linear plots. Therefore, in order to make your plots maximally understandable to the largest number of people, it is best to use a linear axis scale unless there's a compelling reason to use a logarithmic scale. A few additional remarks about logarithmic scaling. First, figure 322 shows the y-axis tick marks being multiples of 10, but other multiplicative factors can be more suitable for specific applications like doubling. This would be having tick marks of 2, 4, 8, 16, 32, and so on. Second, logarithmic scaling is generally used for positive valued data because of difficulties with multiplying by 0 and, depending on how the data are transformed, negative numbers. Third, it is possible to use logarithmic scale for the x-axis. When both axes are log-scaled, the plot is called a log-log plot. Section 310, Discretizing Continuous Data. There is a dark side to discretizing continuous data. I will briefly introduce the issue here because it is relevant to histograms. Then I will continue the discussion later in the book because discretization is relevant for deciding whether to perform an ANOVA or regression and for visualizing data in a regression analysis. Now, the next several paragraphs of text refer to figure 323. So let me take a moment to try my best to explain what is going on in figure 323. There are two panels, A and B, and each panel contains a scatter plot of data on the left and a histogram of those data on the right. These are all stylized data. These are fake data used for illustration purposes. So in panel A, in the scatter plot, we see the x-axis has data index, so it's just the arbitrary ordering of data points, and the y-axis is the data value. There are approximately 20 data points shown in this scatter plot, and there are bars or ribbons, horizontal ribbons stacked on top of each other. There are 8 of these ribbons with different shading of grayscale, and this indicates the boundaries used to create the histogram that you see on the right. So the number of data points that are between the first boundary are shown in the leftmost bar and so on up for all of the bars. So the idea is that all of the data points that are contained within the specific boundaries corresponding to one bin are counted, and that is the height of the bar in the histogram to the right. Now, panel A is titled Data Values Are Similar Within Bin, and that's because the number of bins is relatively high compared to the number of data points. Panel B shows a similar organization and is titled Data Values Are Similar Across Bins. And what you can see in panel B in the scatter plot on the left is that there are 2 data points. One is a square and one is a triangle that are numerically very, very close to each other. And yet they are separated by a boundary, so they are included in different bins. In contrast, there are 2 triangles, one upward pointing triangle very close to the boundary and a downward facing triangle very far away from the boundary. Those are in the same bin, but they are numerically very far apart from each other. The figure caption reads, Illustration of a danger of discretization. Close by data values like the square and the up-pointing triangle can be assigned different bins while further apart data values, the up and down pointing triangles, are assigned the same bin. Back to the text. To start the discussion, consider figure 323a, which shows a visual illustration of how histograms are created. The range of data values is segmented into equal-sized bins, that's the scatter plot on the left, and the number of data points within each bin is counted to create the histogram in the right panel. Now imagine creating a histogram using only 2 bins. This is called binarizing the data because the data are transformed from continuous into 2 categories. This is panel B that I explained. Although many data values are similar within each bin, there are many instances of data values being closer to each other across bins compared to within bin. For example, the square and up-facing triangle are numerically close to each other, but are in different bins, while the square and diamond are numerically further apart yet in the same bin. Same story for the up and down-facing triangles. Thus, the risk of binarization is that many data points between categories can be closer to each other than data points within category. This violates an unwritten assumption of interpreting histograms, which is that the data within a bin are sufficiently homogeneous that it is valid to reduce them into one bar. You might think that this is an extreme and unrealistic point. Indeed, why make a histogram with only 2 bins? But this is not merely an academic exploration. Binarizing continuous data is often done in practice. For example, a median split of the data. The conclusion here is that discretizing continuous data can be appropriate and can be used to simplify data analyses, but should only be done with careful consideration of the potential impact of that discretization. Section 311, radial plots. Radial plots, also called polar plots or spider plots, are a way of visualizing circular or cyclic data. Circular means that the values keep wrapping around, like the hours of the day or the days of the week. To create a radial plot, data categories are positioned equidistantly around a circle, and the radial axis, which is the distance from the origin, represents the data magnitude, and that is equivalent to the height on the y-axis in a bar plot. Figure 324 shows an example of a polar graph depicting the average temperatures of the year. This is clearly an appropriate application of a polar plot because the end of the data series, which is December, naturally flows into the beginning of the data series, which is January. So figure 324 shows a polar plot. It is a circle that is cut up equidistantly. You can see January to the left, and then February above and to the right, and March and April and so on, all the way around to December, and then cycling back into January. It looks like a clock, and the hours on the clock would correspond to months of the year. The radial axis, the distance from the origin, is degrees in Celsius, and the title of the graph is High Temperatures Near Patagonia. And what you see, the data plotted inside the graph, are the average temperature, the average high temperatures recorded near Patagonia. It is the highest, so the furthest away from the origin around December, January, February, and closer to the origin around June, July, and August. Back to the text. Radial plots should not be used on non-circular data. Furthermore, radial plots cannot be used for negative valued data because the distance from the origin is a non-negative quantity. Figure 325 shows an example of inappropriate use of a radial plot. The circular axis contains movie genres, and the radial axis shows my preferences for those genres on a scale of 1 to 10. So figure 325 is another polar plot or radial plot, just like I described for the temperatures near Patagonia, except here the categories around the axis correspond to different movie genres like horror, documentaries, action, sci-fi, and so on. And the data values inside the plot show my personal preferences for each of these genres. Back to the text. There are several reasons why radial plots should not be used on non-circular data. I invite you to think of some reasons on your own before reading the next paragraph. One reason is the same as why lines are inappropriate for bar plots with categorical data on the x-axis. The lines give the impression that there is an interpolated data point between, for example, rom-com and horror, and that just makes no sense. Of course, a movie can contain both elements, but the categories are not amenable to mathematical manipulations like with numerical data. You can contrast this with figure 324, where an interpolated data point between September and October does make a lot of sense. For example, the third week in September could have an expected high temperature of 18 degrees, which is somewhere in between the average for September and the average for October. A second reason is that the categories are not circular for the same reason that category ordering in a bar plot is arbitrary. It just doesn't make sense to cycle from rom-com through anime back to rom-com. There is nothing intrinsic to the data that requires this ordering or suggests cyclicity. Again, compare figure 324, where the order of the months and their cyclic nature are intrinsic to the data. Now, despite the arguments above, you will see quite a few inappropriate radial plots in your adventures through data science. As I've written before, there are so many things to worry about in human civilization that we can forgive such minor violations of good statistic etiquette. But please do not contribute to the bad practice of using radial plots when they are inappropriate. Section 312, Color. Color in graphs is a simple and powerful, and yet potentially risky way to make visualizations more appealing and informative. Adding color is simple. Especially in Python or R, adding color is as simple as specifying the palette to use. You can find visual lists of color palettes with a quick web search, or directly specifying the colors of the plot objects. In most matplotlib functions, color is specified using 3-digit parameters such as color equals RGB, where R, G, and B are floating point numbers between 0 and 1. You'll see that in my code for this book, I almost always keep these numbers equal, which produces grayscale lines. Color is powerful. There are several mechanisms in the brain that preconsciously orient us to color. The superior colliculus, one of the first targets of neural impulses after the retina, responds to changes in color and can directly control eye movements to a patch of color. And there are entire regions of the cortex dedicated to processing color. Basically, we are hardwired to look at color, so adding color to your graphs will engage automatic brain attentional mechanisms. Color can also add another dimension of information to your graphs. This is the idea of a heat map, which shows multivariate data such as correlation matrices, which I will discuss in Chapter 12. Color can also help separate multiple lines on the same axis. Color is risky. Adding color to your graphs comes with 2 risks. The first is that you cannot know the quality of the visual image that your audience will actually see. If your graphs are shown in presentations and to a live audience, it is possible that the colors are distorted by the projector or by the screen. If your graphs are online, people might view them from a reduced visibility condition, such as a small phone screen or in bright sunlight. The second source of risk is that even if your audience is sitting next to you looking at your screen, you cannot guarantee that they will experience the same colors as you do. In fact, color blindness occurs in around 8% of men and 0.5% of women, according to a Google search. Many people in particular have difficulties distinguishing subtle shades of red and green. I do not mean to dissuade you from using color. Color is a great addition to any visualization and should be used as much as possible. Instead, my advice is, when possible, use color as an addition to a plot, not as a crucial feature without which the plot is uninterpretable. One example is to make color redundant with luminance or line style. For example, light green solid lines and dark red dashed lines differ in color, but can also be distinguished even in grayscale viewing due to differences in brightness and line style. Section 3.12.1, Which colors to use. Color theory and color in data visualization is a hot-button issue, meaning that there are people, so-called data visualization purists, who express very strong opinions about which colors and which sets of colors can and cannot be used in data visualization. The color map JET is perhaps the best example of the ire that this discussion has elicited. Don't take my word for it. Search the web for, quote, "Should I use the JET color map?" end quote. I do not have a strong opinion about this issue, and I don't make the effort to engage in a protracted debate. There is much discussion, experimentation, and theory about colors and human visual perception. If that topic piques your interest, then I fully support your quest for knowledge. Otherwise, you can just use one of the many color palettes that come with Python and R visualization libraries. You can also find color palettes online. Two websites that I use are colorhunt.co and color.adobe.com. Section 3.13, Exercises. I am actually not going to read all of the exercises in this audiobook because I present the exercise instructions and an overview of my code solutions in YouTube videos, which are available online. You can find them from my YouTube channel, or you can go to the GitHub website for this book, where you download all the code, and there is a direct link to those YouTube videos. However, I will read the first paragraph of this section, and it goes as follows. A quick reminder of what I said in Chapter 1. These exercises are your opportunity to explore concepts in statistics using code. I hope you see them not as tedious work to labor through, but as inspiration to continue coding and experimenting on your own. These solutions are not printed in the book, but they are all available at github.com/MikeXCohen/statistics_book. End of Chapter 3.